All right. Good evening and good morning, everyone. I'm Jingfeng, a researcher from Riken AIP. Today, I'm going to host the TrustML Young Scientist seminar. Before that, allow me to briefly introduce our Riken AIP to our valuable guest. The full name of Riken AIP is the Riken Center for Advanced Intelligence Project. AIP was founded in 2016 as the Research Center for the MAX AIP project. AIP conducts Japan's leading AI research, which is headed by Professor Sugiyama. We aim to enhance AI fundamental technologies and its real-world applications. AIP encourages the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. Next, let me briefly introduce our today's speaker. Rui Han is a PhD candidate in the Computer Science Department of Cornell University. She is advised by Killian. Before Cornell, she received her bachelor degree in computer science from Yale class in Tsinghua University. Her broader interests are in trustworthy machine learning. Recently, she focused on differential privacy, federated learning, and distribution shift. Let's sincerely welcome Rui Han to give us her talk on adaptation to label distribution shift. Yeah, Rui Han, please get started.
Yes, thanks for the introduction, and hello everyone. I'm Rui Han Wu, a PhD candidate at Cornell. Thanks for coming to my talk. So this talk is based on the joint work with Chuan, Yi, and Killian. So label shift is a certain type of distribution shift. Think about this example of code flu classification. In the data generation process, the direction is from the label to the feature, and the symptom occurs to the patient after he or she gets the exact code or flu. Another example from the label to the feature is sentiment analysis. The sentences are written from the one who is positive or negative, which is the label. Then with this data generation process, one reasonable assumption is that how to generate X from Y. If then we will assume that this generation process is invariant and it's decided by the data's property. And this is the key assumption of label shift. Here is the formal definition. QXY is probability density function. The conditional distribution QXY is fixed, while the marginal distribution of label QY can shift. Then I will show what is online. The left paradigm shows the typical offline setting. We assume that all test data are sampled from a fixed test distribution, and they are together given to the learner. And the right figure shows the online setting. Patients would come one by one over time, and the distribution of cold and flu would change gradually from the non-flu season to the flu season. In the online setting, the learner is allowed to adapt the model over time. Model F0 before the online process. In the example of flu code classification, this model would be trained from non-flu season. And then at time t, suppose the global cold and flu distribution is QT, and the patient then at this time comes to the hospital and is represented by a symptom vector xt. Formally, the nature provides xt, while xt is sampled from an underlying distribution qt. Qt here is label shifted from Q0. Then the current model FT makes the diagnosis for the patient XT, which could be flu or cold. And finally, at the end of time t, the learner updates the classifier to ft+1 according to any algorithm, any designed algorithm A, with the input of the initial learned model F0 and all previous observed symptom vectors x1 to xt. And this updated classifier will be used for the next time t+1. Okay, so any questions so far for the problem setup?
Excuse me, I want to know the definition of the label shift further. You say that at the beginning, the conditional distribution of y is fixed, right?
Yes, x given y is fixed. Say, if we know this patient gets flu, then the symptom vectors is sampled from a certain distribution, a fixed distribution.
Okay. So as you say in the online learning setting, this conditional distribution is updated, or the total distribution QXY is updated?
Oh, yep. Okay, here we go. Yes, so here we assume that this conditional distribution wouldn't change over time, but the label distribution would change. So in the example of flu cold classification, right? So from the non-flu season to the flu season, the percentage of flu would increase. However, we still assume that the symptom vectors given what the patient is flu or cold is fixed, wouldn't change over time.
Okay. So the conditional distribution is updated, right?
Is fixed. The conditional distribution is fixed.
Conditional is fixed, and the total distribution QXY is updated round by round.
Yes. Yes.
Okay, thanks.
Yes. Thanks for asking. Any more questions?
Hi. I also have some questions. So, how often are you going to update the classifier? So, I think in practice, how often or how large each iteration is often a significant problem, because updating a classifier it can consume some computation or time. So so I know this is an abstract formulation, but I wonder what's your thoughts about that size of each iteration.
Yes. Thanks for asking. So in this formalization, we focus on at each iteration t, we only receive one single data point and make the updates. However, once the algorithm is introduced, it's easier to adapt it to the case that at time t, you can receive a batch of data and you only update once for this batch of data.
Great, thank you.
Yep, and the difference is that the variance of the performance would be different. So if you will receive more data in the SAMT and update the model with this batch of data, then the variance of performance would be smaller than the single data version. But in expectation, we will see the conclusion. They are the same.
Great, thank you.
There's also a question in the chat box. Can you read?
Wait, how to open the chat box? Let me check. Oh, I see. Sorry.
Yeah, please.
Yes, that's the good question. So, yeah, the question is that are we going to update the classifier without the knowledge of true label? And this is actually the key definition in our framework. And the answer is yes, we wouldn't assume that we will receive the label for the XT during the online process. And we will only do the unsupervised update. Yeah, thanks for asking. And indeed, this is the point that I will introduce next. So I guess we can continue. Here we go. So this framework is very similar to the traditional online learning, but the key difference is that we don't have the access to the loss function. We only assume that we receive a sample XT at time t without any supervision. But first, let things easier. Let's see what we can do with the knowledge of loss. So the loss function is defined as the expected 0-1 loss here. And we also define the regret function for the whole online process, which is the average of loss over time minus the minimum average loss achieved by any fixed classifier. Then if we assume the learner has the knowledge of Qt in the fifth line, then the loss function is queryable. So given each f, since we know the knowledge of Qt, we can compute the loss and also query its gradient. So if we can compute the gradient with respect to the model f, then we can use the gradient descent to update it. Here we show the formulation on the left. This is called online gradient descent. And with some good properties such as the convexity, the regret will be guaranteed to be arbitrarily small when the iteration t is large enough. So this is the case that we know the loss function. We can receive the supervision, receive the signal during the online process. And this is then we can apply the traditional online learning algorithm, online gradient descent, and the problem is solved. Then back to our framework that only receiving a sample XT. And fortunately, we can construct an estimator for the loss and its gradient, which will reduce this gap to the traditional online learning. Okay. Continue. So then I'm going to introduce this reduction. So let's start by introducing the confusion matrix. So confusion matrix is defined for a classifier F and a distribution Q. Here is an example of flu code diagnosis. This value 0.12 means that when a patient gets flu, the probability that this classifier F predicts it as cold, this probability is 0.2. Then at the first step, we can rewrite the loss function. The first equation is basically the definition of the loss. And then by the law of total probability, this loss is equivalent to the weighted average of error among each class. So the second term in the summation is the error for the class I. And next, because in the definition of label shift, this conditional distribution wouldn't change. So we can replace the Qt by Q0. And finally, we write it in the form of this confusion matrix from distribution Q0 and the vector of marginal label distribution. So Qt here is a vector with the length of total classes M here. And the value on I is the probability that the label is I. So this is the first step of rewriting these loss functions. If there's no question, I will move on. Okay. And then let's first assume that we have the knowledge of Q0. So with this assumption, look at this loss function. Once we know the Q0, then the second term in this loss function is also accessible. Then the only missed term is Qt. We don't have the access to this Qt. And then in the second step, we will construct the estimator for this Qt. So first, denote this Qt prediction as the vector to indicate the distribution of prediction F0xt, where xt is sampled from the marginal distribution Qtx. So in the example of code and flu classification, this Qt prediction means that if at time t there are a lot of patients comes to the hospital, then what percentage that we will diagnose it to code, and what the remaining percentage that we will classify it to the flu. So it is a vector with the length m. And then one fact implied by the definition of confusion matrix is that Qt prediction is equal to the multiplication between the transpose of the confusion matrix and Qt. Or equivalently, this Qt is equal to the inverse of confusion matrix times Qt prediction. This form is derived by the literature. And thirdly, it's easy to check this one hot vector E F0xt. This is one hot vector with the only value 1 on the dimension of the prediction from F0. So this is an unbiased estimator for Qt prediction. So finally, we can plug in this unbiased estimator for Qt prediction and get an unbiased estimator for Qt. Okay, so in the second step, we construct this unbiased estimator for Qt. Then together with the first step, if we have the knowledge of Q0, we already have access to the unbiased estimator for the loss function. So any questions for this reduction? Okay. So similarly, an unbiased estimator could be constructed for the gradient. So you can check, right? If we want to get the gradient with respect to the model F, with this rewritten loss function, only the second term with that confusion matrix has the model parameters f. And then because we have the access for its value, if we assume we know the knowledge of Q0, we can also get the gradient. And this is again an unbiased estimator for the gradient. Okay, then this is good. Since we know we have an unbiased estimator for the gradient, we can perform online gradient descent. But we just assume that we have the knowledge of Q0. And this assumption could be relaxed to assume we have enough data sampled from Q0, which is more practical. With this relaxation, we still approximately have an unbiased estimator for the loss and the gradient. So because if we have a bunch of data sampled from Q0, we can approximate the confusion matrix by feeding those samples to the classifiers. And for the gradient, because we only have the zero order query for the confusion matrix value, so we can numerically use the finite difference to approximate the gradient. So any questions for the algorithm?
Excuse me, I have a question.
Yes.
Firstly, you mentioned that this online learning setting is different from the traditional setting. So
yes.
Actually, in this way, we also consider the regret to measure the performance of algorithm, right?
Yes.
So what is the comparator term in this regret?
Oh, okay. Sorry, let me. Yep, so the second term here in our definition, this is the minimum loss achieved by an unchanged classifier.
Okay.
Yes, yes. So,
okay, please.
Oh, sorry. Oh, sorry, you go ahead.
Okay. And then here you mentioned the approximately unbiased estimator here in the last step. So I want to know more thing about the approximation here. So how to approximate, and if we used approximately unbiased estimator, what will affect to the reduction?
Yep. So are you asking the detail of these constructions, or how we?
Yes. How the approximation have some effections on the final reductions or analyze?
I see. I see. Sure. Okay. So so the first step, this written loss. If we assume we have the knowledge Q0, then the second term here, 1 minus diagonal of this confusion matrix is known to the learner, right?
Yeah, yes.
Yes, and then the remaining question is how to estimate this QT.
No, I mean,
so,
you say if we don't have the knowledge of Q0.
Oh,
then
I see. I see. Got it. Okay. Yes. So here the formula in the last line, this is the overall estimation for the loss function. So you can see the one hot vector EF0xt. It's easy to get since we can use F0 to make the predictions on XT. But the remaining two are related to this confusion matrix CF Q0. So if we don't assume that we have the knowledge of Q0, so what we can do is that say you have a set of data with label 0, right? And then you can feed them to the classifier F0 here, and then use F0 to make the predictions. Then you will get a probability vector that what the percentage that this F0 predict them to label a class 1 or class 2, followed by the definition of confusion matrix. And if the number of samples is large enough, then this approximation error would be smaller.
So yes, so it depends on the size of the sampled data of Q0.
Yes, yes.
And this information is given in advance to the algorithm, not during
Yes.
the process.
Yes.
So okay, thanks.
Yes. So for example, in the sentiment analysis example, we have a data set collecting all historical data. And then we can treat them as a data set we can use for the training in advance, also for the estimation for this confusion matrix. And then we can process our online algorithm for the future.
Okay, thanks.
Yes. Yes. Okay. Thanks for asking. And actually, I have one more comment for that regret. Did I mention that? Yeah, so for this regret, since the second term we define is the minimum loss achieved by an unchanged classifier. So which means that this regret could be negative. So the minimum of this regret is not 0. Yes, and one more comment for this for the data sample from Q0. Actually, we can relax this assumption more by we don't need all data sampled from the same distribution Q0, but we only need that they are sampled from some distributions which have the same conditional distribution. Because their confusion matrix are all the same, so we can use them together, even though they are sampled from different Q. We can use them together to approximate this confusion matrix, their sharing confusion matrix.
Excuse me, may I have a question?
Yes.
Thank you for your interesting sharings. I'm wondering that in your derivation, you assume Q0. You start by assuming Q0 is known, and then you have somehow a method to estimate Q0. So my question is, can this intuition and the derivation modify to hold for any QT? Because, for example, during the flu season, we have a bunch of patients brought in the hospital, brought in the medical system during that short period of time. This means for some specific QT, you will have a bunch of number of learning examples available. So that if we can modify your derivations for any QT, then we somehow can leverage the iteration where we have many observations to build a better online learner. Is this possible?
So are you asking that if we also have the labels for during the online learning, can we do better?
No. I just want to fix on your setting. and
Mhm.
change the analysis from Q0 to any QT.
So you are saying that, so here we assume that we have enough data sample from Q0, but then you change it to, we can also collect data from QT.
Yes, sort of.
I see. Yes. So here we should. So for this assumption, we assume that this data sample from Q0 is labeled. So because we should know the label, otherwise we can't estimate the confusion matrix. So if we fix this assumption to any QT, then that will change the setting a little bit, because then you may assume that you also receive some label data at time t.
Oh, I see. So the key point for the analysis starting at Q0 is that you only require label data in iteration 0, right?
Yes, from before the beginning of the online process.
You have this label data for as a starter, right?
Yes, yes, yes.
Oh, I see. Thank you so much.
Yes. Yeah, thanks for asking. Any more questions? Okay. So in summarization, with a pre-hold dataset D0 sampled from Q0. So this dataset is label data. We collected before the starting of online process. We can perform online gradient descent by updating the parameter QT, theta t. And so if we assume that this loss function is convex in theta, then the regret converges to 0 in the rate of 1/√t, which means that when t is large enough, then your average loss wouldn't be much worse than the loss achieved by any unchanged classifier. So this is the summarization of our algorithm, and then I will move to the experiment result. Okay. So first we conduct our experiment under the simulated shift. So we choose two classes from CIFAR-10, represented by the green and blue lines here. And then we consider 4 different types of shift. The constant shift, so the margin distribution of labels wouldn't change over time. And the monotone shift, it increases and decreases linearly. And this periodic shift, and also the exponential periodic shift. So we will train a ResNet 18 network on the training set as the initial model F0, and then during the test time we feed the online process by the test data in the test split of CIFAR-10. Yep. So in this page, it's about the hypothesis space. Since previously we didn't introduce it. So in this experiment, we particularly consider a reweighted classifier, which means that once you have an F0 trained at the beginning, we only reweight the predicted weights by some parameters theta. So see the examples in this rectangle of how this reweighted classifier looks like. So suppose we have a symptom vector X, and the probability, the weights predicted by the F0 is 0.2 and 0.6. So the predictions right now would be code instead of flu. And then we suppose that the initial label distribution is balanced, and the to be applied reweighting parameters, this theta is 0.8 and 0.2. Then we process the reweighting. And after the reweighting, the predictions of this reweighted classifier becomes to flu instead of code. And moreover, I didn't present it here, but in our paper, we justify the convexity of this hypothesis of this theta empirically. And then here are two baselines. The first is that we don't adapt or update our classifier. We use that initial classifier F0 for all time t. And the second is that we present the value from the second term of regret, which is the minimum loss achieved by a constant classifier. So this table shows the average losses, the error for the different algorithms under the 4 shifts. So we can check that first, the online gradient descent achieves significant improvements compared with the base classifier, which means that the updating helps for the adaptation. And moreover, we can compare the online gradient descent and the optimal fixed classifier. So we can check that for most cases, the performance of OGD matches the optimal fixed classifier. And for some cases, so we can take a look to the exponential periodic shift. It's even smaller than optimal fixed classifier. So in this case, the regret is negative. So this result justifies the theoretical guarantee we have from the online learning from the previous analysis. And moreover, we experiment with a real-world dataset, archive. So we collect papers on archive in the past 20 years, 30 years. And then we, the feature vector we use is TF-IDF vector for the abstract, paper abstract. And the task we will do is to predict the subcategory for each paper. So the subcategory contains the computer vision, the machine learning, the robotics, and the computational language. So this archive data set is sort of under the assumption of label shift. So because once you choose a topic lying in the computer vision, then you will write an abstract from this topic. And the distribution of categories indeed changes over time. So the left figure shows 4 main categories, how they change over times. And the right is the result table. We can get the similar conclusion from the simulated shift experiment results. So the OGD is mostly the same as optimal fixed classifier, and they are all better than the base classifier. Okay. So in conclusion,
Excuse me, may I have a question on this experiment?
yes.
So do you explain what X is here?
Yes.
So what is the feature space here?
Yes. Sorry. Yeah. Maybe I describe it too fast. So you can check the second bullet here. The feature we use is the TF-IDF vector of each paper's abstract.
So is TF-IDF a very long vector of words?
So it has the same length. So the length of it is the size of word dictionary.
Oh, I see.
Yeah. So it's very similar to bag of words feature vectors, but it's normalized by the word frequency on each dimension.
I see. The reason why I ask this question is that in your motivative example, I'm convinced that the flu and the cold has a shared set of symptoms as the feature, right? Although
yes,
the feature value will be different from flu and cold. So this is totally acceptable. So when I encountered this experiment, it gives me a question that, for example, the computer vision and natural languages, they will probably share different feature space, right?
So you are saying yeah.
But in TF-IDF definition, the dictionary words are fixed. So in this way, we can view it as a common base for the feature space.
Yes, yes.
I see. Thank you so much.
Yes. So in the way that we construct this data set, so here we collect 30 years papers in the history, and we split it by some time point and treat all papers before that time point as our D0, as our pre-hold data set. And then we build the word dictionary from that D0 and define how to select the words, define that feature space from D0 as well. And then for the papers after that time point, we use that already defined feature word dictionary to process this TF-IDF vector.
I see. Thank you so much.
Yes. Yeah. So the reason why we didn't experiment with cold and flu example is that that data set is really hard to find because we need a data set with the time label. So we only find this archive meeting this requirement, and also potentially have hold the assumption of label shift. So in conclusion, we define what is the online label shift, and we came up with an algorithm to adapt the classification model without receiving any labels in the online process, which is done by making the reduction from this unsupervised setting to traditional online learning. And we evaluate our algorithms in the experiment, and the results shows the same conclusion. consistent conclusions and also justify the theoretical analysis that we have for the algorithm. Yeah. And that's all for the talk.
Thank you very much. Hello, audience. If you have a further question, please feel free to ask.
Excuse me, I have a question.
Yeah. Yes.
As you mentioned, I think during the talk you say the regret about the lower bound. You say that the regret can be negative in your case.
Yes.
But for the traditional online learning, we say that, for instance, for the binary prediction case, the regret, there is a lower bound as square root of t, right? So I want to ask you the question that why you say that the lower bound here is negative. There is not a, I mean, for the traditional case, there is a square root t lower bound here.
So how does that lower bound statement exactly state? So is it actually in states that the convergence regret the convergence rate wouldn't be better than this one over square root t?
No, could you please say the in your slides the definition of regret here?
Yeah. Yeah. Let me go. This page.
Yes,
right?
yes. You can say the regret function here.
Oh.
You divided capital T in the regret. Now, if
Yes.
we multiply capital T, then we can say the regret there is a upper bound as square root of T.
Yes.
And usually, I think you must be very familiar that there is a lower bound, also theta, omega square root of T here, right?
Is it true?
Oh, of course, this lower bound depends on that. When the algorithm gives a prediction, then the environment could select some loss vectors.
Oh, I see. So let's see.
For instance, you say like online learning prediction with expert advice. The regret is very tight. There is a theta square root of T, right?
Yes. So I think that bound is not saying this regret can be smaller
so
than
why
that.
Why it fails here?
Yes. So I think that conclusion is stating that this convergence rate at worst case can be better than 1 over square root T as well.
Yes.
So which means that at some case you can be better than that, but you can't be better than 1 over square root T for all cases.
Yes.
For all online processes.
Mm-hmm.
Yeah. So or in the other word, so we can figure out maybe some sequence of QT here, such that the regret wouldn't be better than 1 over square root T.
Yes. So
yes.
So I want to know that do you have some conclusion or result consequence for your regret lower bound issues?
Okay. So in the theoretical aspect, that lower bound means that not all online, not in all online settings that this regret can be converge better than this rate. Or in the other word, it says that in some cases you can be better than this rate, but in some cases you can't. And this argument can be justified in the experiment result. So you can check here, right? For the first 3 types of shift, the OGD indeed is not better than the optimal fixed classifier, which means that the regret is positive for these cases. But only for the last two columns, the regret is negative.
Oh, okay. In theoretical aspect, you did not or not yet to give the lower bound of the result.
Oh, I see. So you are saying, can I find a sequence of QT such
Yes.
that we can do better?
Yes.
Oh, yes. Sorry. Yeah, we didn't have that result.
Okay.
Yeah.
And furthermore, have this result published somewhere, because I would like to see the paper.
Yes.
After
Thanks
the-
for your interest. Yeah, it's published in Neurips last year, 2021.
So the title is same as here, right? Online
Yes.
adaptations. Okay, thanks.
Yes. Yes. Thanks for your interest. And I have one more comment about this regret. Yeah, since in this definition of regret, sorry, let me back to the definition. In this definition of regret, it's possible to be negative, but we can define a dynamic regret. In that dynamic regret definition, the regret can't be negative. It's positive. It's always non-negative. And there is a follow-up work, not from mine, from other people. They come up with another algorithms to reduce that dynamic regret. Also have the convergence.
Is there any further constraint for the I think
dynamic
because
regret?
yes, because generally in traditional online learning, the dynamic regret, if there is no constraint of the loss sequence, it cannot be
Yes.
convergence, right? So is there
Yes.
any further constraint for that
Yes.
work? I think
yeah, I think they may assume that for example, the QT here wouldn't change very suddenly, so it will change in smoothly with some factor such that they can have that derivation.
Okay, so totally speaking, that there is a very similar result to the traditional online learning models,
Yes.
right?
Yes.
Okay, thanks for
Yes.
your thanks for your work. Thanks.
Yeah. Yes. Okay. So any more questions?
Excuse me.
Yes.
I think I'm still interested with the QT setting. So if you are, so currently in your model, you assume there is a data set for you to calculate QT, right? Q0, right?
Yes.
And if we modify your formulation a bit so that the learning agent can autonomously query, say, for at most 5 Ts. So in this case, the learning agent has the freedom to query 4 other iterations, to query for labels of data in 4 other iterations. So under this relaxed formulation, do you want to do the query? And if you do, what would you utilize those query points from this additional data point collected? Thank you.
Yes. So if we can have the labels for some iteration, so you are saying that there is some mid state between totally unsupervised and the supervised setting, right? So we may have labels for some samples for some time t. How can we
Yes.
utilize those samples and how it helps?
Mm.
Yeah, so we can take a look to this update.
Yes.
So if we have more label data, one improvement could be the approximation for this confusion matrix. Because we have more data, then the estimation for this confusion matrix would be more accurate. So this will improve in practice, but it wouldn't be reflected in the theoretical result, since in theoretical result we ignore such approximation error. But the more label samples can also help with this one hot vector here. So for the estimation of Qt. So because right now in the second step we construct this unbiased estimator of Qt by this confusion matrix and the one hot predictions. But indeed, if we can have the label, then the one hot vector with that label is also an unbiased estimator for this Qt, and which likely have smaller bias than this Qt on the slides.
Excuse me. So a smaller bias is from the more accurate one hot estimation or from the confusion matrix?
So if we can have label data, we don't need the confusion matrix anymore. We can that label is the unbiased estimator for the Qt, right? Because this label is sampled from Qt. Yes. So if which means that if you have label, you can use this label to construct this unbiased estimator. And if you have more data at the same time t, we discussed at the beginning of this talk. So say the case that at time t, what if we receive multiple data points at the same time? So that multiple data point will also reduce the variance of this estimator.
I see. Thank you so much.
Yes.
This is really interesting.
And that variance, so you can check that for this theoretical result. Indeed, there is an expectation before these losses. I didn't add it here. But in the paper we have that expectations. So in expectation, whatever unbiased estimator you have, the result for the expectation would keep the same. However, we can discuss the variance of this result, and more label data will help with that variance.
I see. Thank you so much. Thank you for pointing out these details.
Yes, so thanks for asking. Yes.
Okay. All right. This is a good time. The talk is very interesting, attracting a lot of questions. And thank you very much again for a really great talk. Hopefully in the future you can visit us physically in our center. Thank you.
Yeah. Yes, thanks for the discussions. And if you are interested, we can discuss more through emails, or if you have any more questions, you can shoot me an email. Yes.
Sure. Okay. This is the end of today's seminar. Bye-bye.
Yeah. Thank you, everyone. Yeah. Bye.